All right, guys, here we go. The last section, or the last test material. All of this test is going to be on waves. Okay? So I always end with waves because this is kind of fun stuff and talks about light and sound, and these are things that most people are familiar with in their everyday life, and they have fun with this one. So this is chapter 16 in your book. It starts on page 421, okay? And we're going to be talking about the wave model. And these are properties that all waves have in common. And then we're going to move out to talking about sound waves and light waves, okay? Now, the wave model is built around a traveling wave. By definition, a traveling wave is an organized disturbance traveling with a well-defined wave speed. We categorize waves according to the way the wave waves. I know, it sounds funny. Or what the wave is moving through. So we could talk about water waves, or sound waves moving through the air, or we could talk about light waves, or we could talk about earthquakes and the way the waves move through the dirt. Okay? Now, if we talk about the way a wave waves, we'll either talk about transverse waves, or we'll talk about longitudinal waves. So let me pull this back down. I'm fighting. Okay, now a transverse wave is one in which the displacement or disturbance is perpendicular to the direction the wave is traveling. So if you think about moving a rope up and down, and then that disturbance moving along the rope, so the motion of the rope is perpendicular to the direction the wave moves, that's a transverse wave. So when you pluck a guitar string or you strike a cymbal, you actually are creating a transverse wave in the string or the cymbal. Okay? Now, a longitudinal wave is one in which the displacement of the disturbance is parallel to the direction the wave is traveling. This is called a compression wave. So if you think about a spring, and you think about doing back and forth with the spring, then compressions actually move down. You can try this with a slinky. Now let me see, I should have a slinky here, and we can see it in the slinky. Okay guys, got a slinky. Okay, now transverse wave goes like this, okay? A longitudinal wave will go back and forth. Let me stop it, okay? So you can see the pieces of the slinky going back and forth. So transverse, up and down, longitudinal, back and forth. Now, when you have a longitudinal wave, we talk about rarefaction and compression. A rarefaction is a region of low pressure, low density. So in the spring, it would be when the spring is stretched out. Compression is a region of high pressure, okay? High density. That's when things are close together. So if it's stretched out, it's rarefaction. If it's pushed together, it's compression. So let's talk about mechanical waves. Mechanical waves travel through a medium, okay? Air, water, dirt, along a string, along the surface of a sheet of glass, along a piece of metal, okay? That would be mechanical. So sound waves, water waves, earthquakes are mechanical waves. Electromagnetic waves is the self-sustaining oscillation of the electrostatic field and the magnetic field that can move through a vacuum. Okay? So here that pesky field pops up again. We have an oscillation in the electrostatic field and the magnetic field. And this is that disturbance in space that doesn't need a medium. Now, light waves, radio waves, microwaves, gamma waves are all electromagnetic. So we're going to start with mechanical waves because it's really easy to think about a medium, okay, something that's being disturbed. So for a medium, for a mechanical wave to pass through a medium, there needs to be some kind of restorative force. A restorative force wants to pull the particles back toward their original position, okay? So they're always pulling it back toward its original position. That means there needs to be some kind of connection between the particles that make up the medium. The stronger those connections are, usually the faster something can move through a medium. The weaker those connections are, the weaker or the slower it moves through the medium. Now, a wave passes through a medium without permanently displacing the particles in the medium. So if you think about my slinky here, okay, if I were to, let's stop it. Okay, I have it here. If I send a pulse, it disturbs things, but everything wants to move back to where it was before. All right? So when you have a wave, it just passes through. Now this is very different from particle behavior, because if I were to toss a ball, the hunk of stuff changes its location permanently. Okay? Now, a wave transfers energy, but does not transfer matter. So the wave transfers, so if you can think about a wave, a mechanical wave is energy being transferred or transported through a medium, but it doesn't require the wholesale movement of a chunk of matter. So, I could use a string, okay, to, vibrating string, let's say, to knock over a cup, and the string would stay where it is. But if I rolled my bowling ball to move it, to transfer energy to it, that would be different. Okay? Now, wave speed is the speed at which a disturbance travels through the medium. The speed of a mechanical wave depends on the medium. The stronger the restorative force, the faster the wave will travel, the higher the wave speed, and the type of wave. So sound waves, okay, light waves move through water differently. Also, if we think about earthquakes, they talk about S&P waves. One is a compressional longitudinal wave, one is a transverse wave. They actually move through mediums at different speeds. For a wave on a string, okay, the velocity is equal to the square root of the tension of the string divided by mu0, which is linear density, which is the mass per unit length. So notice that if you increase the tension, you're going to increase the wave speed. If you increase the mass of the string, you decrease the wave string. So we're going to look at problems 1 and 2 at the end of chapter 16 here. Okay, so I'm going to flip to the end of the chapter. We look at problem 1. Okay, it says the wave speed on a string under tension is 200 meters per second. What is the speed if the tension is halved? So let's go to a whiteboard. Okay, so the wave speed V is equal to 200 meters per second Now remember, V equals the square root of T over mu. And it said, what happens if the tension is halved? So I want V, I'll call it prime, which is going to equal the square root of T, well, 1/2 T over mu. Okay? So if I've got, which is the same as the square root of T over 2 mu. So if I plug things in, I've got 200 meters per second is equal to the square root of T over mu. Let me play with this a little bit. And come down here, I know that what I have is essentially the square root of 1 over 2, the square root of T over mu. So our new V prime is going to be the square root of 1 over 2 times 200 meters per second. Let me grab my calculator. .5 square root times 200. It says that our V prime is 141 meters per second. Okay, so we cut the tension in half, but it didn't cut the speed in half. Okay? All right, now let me erase this. Now let's look at problem 2. Problem 2 says the wave speed in a string is 150 meters per second. Okay? And it says that the tension is 75 newtons. Then it says what tension will give a speed of 180 meters per second. I want a T2 when V is 180 meters per second. Okay? So I know 150 is equal to the square root of T over mu. So 150 is equal to the square root of 75 over mu. So I'm going to solve this for mu. So I square both sides. 150 squared. Okay? And mu is going to equal 75 then divided by 150 squared, which is 3.33 times 10 to the minus 3, and that should be kilograms per meter. Okay? So 180 meters per second should be the square root of T over 3.33 times 10 to the minus 3 kilograms per meter. So I square both sides. So I'm going to have 180 squared times 3.33 times 10 to the minus 3 kilograms per meter has to equal T. So I get T to be 108 newtons. Not bad, right? We can handle that. Okay. Now, we're going to start off here looking at 1D waves. 1D, one-dimensional, which is going to mean that we're going to look at a disturbance that's moving in one direction, that's along a string or a wire or across a slinky. Okay? We can use 1D to set everything up, and then we can apply that to 2 dimensions and 3 dimensions. Now, anytime we talk about a wave, there are 2 variables that we have to look at: time and location. Okay? Now, let's talk about a wave pulse. A wave pulse is a single disturbance that moves away from the initiation point through the medium. Okay? So if we were to look at a string here, and it's going over a pulley, it's being weighted down by your physics book because you decided that's what you want to do with it. If I were to sit here and pluck this string, just come here and go boing, okay, the disturbance would move, that one disturbance would move down the string. That's a wave pulse. Okay? Now, if I just kept here and kept repeatedly plucking it, okay, I would cause something different, but we're looking at a single wave pulse. Now, if we think about that wave pulse, okay, moving through this medium, if I sit here and watch it, at time t equals 0, I would be over here and I would have initiated. And then at time t, at 1 second it would be here, and 2 seconds here, and 3 seconds here, and 4 seconds here. So it's in a different place at a different moment in time. That's why I said the 2 variables are location and time. Okay? Now, anytime we look at a wave, we can look at snapshot graphs and history graphs. A snapshot graph shows the disturbance at an instant in time. So where something is at 1 second, 2 seconds, 3 seconds, 4 seconds. It shows all the locations in the medium and their disturbance at that moment. Okay? The vertical axis is the size of the disturbance, the horizontal axis is position, and always up in the corner you'll have something that says what time it is. So, come on. So this would be maybe y in meters, and this is the x position in meters, and it might say at t equals 2.00 seconds. And it might do this. Okay, that would be a snapshot graph. Okay, so this is a wave pulse traveling on a string. No, you can't create a wave pulse like that. They're doing it just to illustrate. Anytime you have a wave pulse, you have the leading edge and you have the trailing edge. So this is where the disturbance is starting. This is where the disturbance is ending. And the wave is traveling in that direction with a specific speed. So if we were to graph this in a snapshot graph, it would look like this. Okay? Now, if we were to set up a camera and we were to take a picture every second, we get a series of snapshot graphs that would look something like the following. So here it is at time t1 and time t2 and time t3 and time t4. So you can see the wave pulse keeps moving. Now, let's think about our position x1 here. So notice where the disturbance is at time T1, T2, T3, and T4. Okay? If we now look at just a single location in space, and we look at it over time, we get a history graph. Okay? So we're going to look at a history graph in a second. Now, if you look at two of these snapshot graphs, the velocity can look at the, is going to be equal to delta x divided by delta t. So if I were to look at this position, okay, and then the leading edge, and then look where the leading edge was in our next snapshot graph, the difference in position would be my delta x, and the difference in time would be my delta t. Now, history graph shows a single point along the pathway of the disturbance at an instant in time. The vertical axis is still magnitude of the disturbance, and the horizontal axis is time now instead of position. And over here in the corner, it would say x equals, 0.5 meters. Okay? It would have some kind of indication of where you were. Now, one of the things I want you to notice here is that the shape of the graph looks different. Okay? And the leading edge is here, trailing edge is here. Now, look at this graph, and let's look at this one. Notice that they're flipped. Okay? If you look at the shape of the graph, it looks flipped. And in a history graph, the leading edge, where you hit first, and this is earlier in time, this is later in time. Okay? The leading edge, front edge, is earlier in time, the trailing edge is later in time. So they look different. They represent kind of the same wave, but in different ways. Now, anytime we're talking about a wave, we're going to talk about displacement. It's a measure of the movement of each individual particle relative to equilibrium. The maximum disturbance is referred to as the amplitude, and it's given the symbol A. Now, displacement D is then a function of time and location, okay, because we can do two different kinds of graphs. So, displacement is a function of x and t. Most wave sources that we're interested in, instead of giving us wave pulses, give us sinusoidal waves. Those due to some source that's undergoing simple harmonic motion. Okay? So for simple harmonic motion, remember that period is a time for one repeat of the motion. So if you think about it, if we start here and we go up, down, and back up, that would be one period because I got back to my starting spot. And frequency is the number of repeats per second or cycles per second. So frequency equals 1 over period. Amplitude is going to be our maximum displacement from equilibrium. And wavelength is the distance spanned by one cycle of motion. This represents the distance between successive maximums on a snapshot graph. So if I had a snapshot graph here, okay, and we had a sine wave, so let's say this is at t equals 1 second, okay, and this is x in meters, and this is displacement in meters. The distance from here to here, this is our wavelength. The symbol for wavelength is a lambda. Okay? And it's going to be in meters. Now, you could also measure it from here to here. This is also lambda. It's just the distance spanned by one cycle of motion. So it's the distance between repeats of the pattern. velocity of a wave is the distance traveled, wavelength, divided by the time, which is the period. So we can say V equals lambda over T, or V equals lambda F. So, in other words, if the frequency changes, the wavelength has to change, because the speed of a wave depends on what type of wave in the wave medium. Okay? So, the wave frequency and the wave length are inversely related for a specific medium and a specific type of wave. Now, the frequency of a wave depends on the source of the disturbance. And the velocity is medium dependent, therefore the wavelength depends on both of these. Okay? If frequency goes up, then wavelength has to go down. If frequency goes down, wavelength has to go up. Now, if the speed of a wave is 15 meters per second and the frequency is 50 hertz, that's cycles per second, what is the wavelength of the wave? So I can go .0 meters per second has to equal the wavelength lambda times the frequency 50 hertz. So that means that lambda has to equal 15.0 meters per second divided by 50 hertz, and that's a cycle per second. So notice that seconds and seconds are going to divide out. And remember that cycles is a made-up unit. So 15 divided by 50 gives me a 0.30 meter wavelength. Okay? For a traveling wave, a 1D sine wave traveling in the positive x direction, we can get the following history graph, snapshot graph, and equation. So the history graph would look like that, a nice sine wave. So amplitude A, so it goes between minus A and positive A. Okay? Here's the period on a history graph because the horizontal axis here is time. Okay? If x is fixed, then our displacement as a function of time is at x sub 1, our fixed position with time, and the displacement is equal to a sine k x position minus omega t plus phi 0. Okay, we'll talk about these in just a second. Okay? Now here in a snapshot graph, you have to pay attention to what the axes are. Now the horizontal axis is position, okay, instead of time. So that's how I know I've got a snapshot graph. I get something that's sinusoidal again, but now peak to peak is lambda, the wavelength. Okay? I still go between minus x and plus x. This time, okay, time is fixed, and we're looking at x. X is what's changing. Okay? Now, when the wave is traveling to the right, so the disturbance is traveling to the right, the displacement as a function of x and t is equal to a sine kx minus omega t plus phi 0. Now, omega here, the angular speed, also called the angular frequency. Let's remind ourselves about a few things here. Omega equals 2 pi f, or 2 pi over t. Okay? 2 pi f, or 2 pi over t. Now we've done that before, but it's been a while, so just a reminder. because it's been a while since we did circular motion. K is called the wave number. K is equal to 2 pi over lambda. Or it could be thought of as omega over v, the velocity. Phi 0 is called the phase constant, and it represents the disturbance of the wave at a point x equals 0 and time t equals 0. So phi 0 is based on where this wave is at time x equals 0 and times t equals 0. Okay? So phi 0 is the inverse sine of the displacement at position equals 0, time equals 0 divided by a. And phi 0 is going to be in radians. So hint, pay attention to what your calculator setting should be. Your calculator should be set in radians. Now, let's look at problem 10 on page 586 in the textbook. So if we look at problem 10, okay? Let me go over to the whiteboard. Problem 10 says, a wave has an angular frequency of 30 radians per second. So, omega equals 30 radians per second. Okay? And a wavelength, lambda, of 2 meters. Okay? It asks us, what is the wave number and the wave speed? So I want the wave number k and the wave speed v. Okay. Now, let's look at the other screen for a second. Okay, let me go here. We come back up here. Notice that k is going to equal 2 pi over lambda. Okay? So I can get k, and then k is equal to omega over v. So let's switch back over. K equals 2 pi over lambda. So I'm going to have 2 pi divided by the wavelength. So the 2's divide out, so k here is equal to pi. Okay? And k also equals omega over v. So v would equal omega over k. So omega, 30 radians per second, divided by k, which is pi, and that should be in meters. So when I flip this up, I'm going to get meters over seconds. So 30 divided by pi equals 9.55 meters per second. Okay? So, not too bad. Okay, so I'm gonna erase. the way we're traveling in the minus x direction, the equation would change a little bit, okay? It would be a sine kx plus omega t plus phi 0. Notice if it's traveling in the other direction, okay, it's a negative sign. Okay, so there's a difference. You see the negative sign here, it's traveling to the right. And if it's a positive, it's traveling to the left. So, 2D waves move out from a point of origin along a flat surface. So if I had water, okay, then this is water in a pond, but if you had water in a bowl, water in anything, if you were to sit there and just drop things repetitively in the same location in the water, you would see waves moving out in a circle, okay? The crests that we see here are referred to as wave fronts, okay? And they move out from that disturbance. So we get wave fronts. Now, when we're talking about a 2D wave, okay, the equations are going to look just the same as they did for a 1D wave, except instead of talking about it moving in the x direction, we talk about it moving along the r axis, a radial axis. So a line that locates the crest in an instant in time is called a wavefront. And in 2D waves, those wavefronts are going to be circular. In 3D waves, again, we're going to talk about moving along the r axis. We get the same equations that we get for 1D waves, okay? Except now the wave front is a sphere. So a 3D wave is a spherical wave. Light coming from a light bulb is a spherical wave and moves out in all directions. Now, if you are far enough away from a source of a spherical wave, and you see only a very small portion of the wavefront, okay, the wavefront can appear to be flat. So you've gotten such a small section that you've gotten a flat section of it. We call that a plane wave. Let's face it, I'm standing in a building right now that's on a circular earth, but I think, I know it's flat, and that's because I'm such a small section of the sphere, we're down to where it's flat. Light coming from the sun, when it reaches the earth, appears to be a planar wave. Okay? Now, sound waves. Sound waves are the waves that our ears detect. Sound can travel through gases, liquids, and solids. Most sound waves are longitudinal waves, where it has compression and rarefaction. And sound wave is three-dimensional and moves out in all directions. Now we can make speakers and develop cones to try to force the energy in a specific direction, but ultimately sound is a three-dimensional wave. Okay? So if I have a speaker, okay, the way the speaker works is the inside part of the speaker here vibrates back and forth. And that vibration pushes molecules and then it pulls back, so it ends up giving us regions of compression and rarefaction. So individual molecules then vibrate back and forth, and it's this back and forth vibration that gets moved through a region in space. Okay, I'm gonna take a little break here, guys. Be back in a sec. Okay guys, I'm back. The speed of sound in air is temperature dependent because the density of the air changes. If the density of air changes with temperature, then the distance that things have to vibrate before they can kind of pass the bounce on changes. So it also changes the speed at which the particles are traveling because we're dealing with a gas. Now, 20 degrees C, which is around 70 degrees Fahrenheit, the speed of sound is 343 meters per second. Okay? Now, let's mention light. Light is part of the electromagnetic spectrum. It is not a wave that passes through a medium. Okay? It can pass through a medium, but it doesn't have to pass through a medium. Light is the part of the electromagnetic spectrum that our eyes detect. Remember, light is an oscillating electric and magnetic field. The speed of light in a vacuum is 2.99 times 10 to the 8 meters per second. When it moves through air and then into water or glass, it actually slows down. Okay? Now, visible light, okay, is a part of the electromagnetic spectrum that has a wavelength between 400 nanometers and 700 nanometers, and a frequency of 7.5 times 10 to the 14 hertz to 4.25 times 10 to the 14 hertz. Now, looking at this, okay, the visible spectrum is just a small part of the overall electromagnetic spectrum. So, radio waves, AM is down here at a frequency of 10 to the 6 hertz. So, low frequency, but it's a long wavelength. Okay? And as we go in this direction, the frequency is increasing and the wavelength is getting shorter. And there's the small part of the visible spectrum. So microwaves, infrared, ultraviolet, X-rays. Okay? So any type of electromagnetic wave, when it passes through a medium instead of the vacuum of space, slows down. Okay? N is called the index of refraction. It's the ratio of the speed of light in a vacuum and the speed of light in a medium. N is always greater than 1 because it's always the speed of light in a vacuum divided by the speed of light in whatever medium you're in. Okay, so N is always going to be greater than 1. If I'm in a vacuum, I get 1. If I'm something other than a vacuum, I get a number greater than 1. Because the speed changes in the medium, either wavelength has to change or frequency has to change. Since frequency is source dependent, it remains constant. So as a electromagnetic wave moves from one medium to another, okay, its wavelength changes in response to the fact that it is slowing down. So as we go from a vacuum to glass, the speed goes down, the wavelength has to go down. Now, whenever we talk about a wave, we can also talk about an intensity of a wave. We usually talk about intensity of sound waves and light waves. I, the intensity, is the power divided by the area that the wave is spread out over. Okay, so remember sound waves and light waves are 3D waves, and your wavefront is a spherical surface. So I, the intensity, is P divided by A, the area. So the intensity is going to drop off with distance. So if we know we're dealing with the area as a sphere, that tells us get a highlighter here. That doesn't work very well, does it? I, the intensity, is P divided by 4 pi r squared. So if you know the distance you are from the source of the wave, you can calculate its intensity. Okay, if you know the power at the original location. Now, if we're dealing with a laser beam, we calculate I as P over pi r squared. Because remember, a laser doesn't spread out, okay, like other waves. Now, let me erase. So, if we start looking at the relationship between intensity and position, okay, notice that intensity goes down as a function of r squared. So if I know the intensity at a position I1, and I want to know the intensity at a position R2, then I1 over I2 equals R2 squared over R1 squared. You can flip that upside down and say that I2 over I1 is going to equal R1 squared over R2 squared. So we're going to look at problem 34 at the end of the textbook. Okay, it says the intensity of electromagnetic radiation from the sun is 1.4 kilowatts per meter squared. So I'm given I is equal to 1.4 kilowatts per meter squared. Okay, just above the Earth's atmosphere. 80% of this reaches the surface at noon on a clear day. Okay, so 0.80 on a clear day at surface. It says how much energy will be transferred to your, suppose you think of your back as a 30 centimeter by 50 centimeter rectangle. How many joules of solar energy falls on you as you're working on your tan for 1 hour? So the area we're dealing with is 0.3 meters by 0.5 meters. And we're talking about a time of 60 minutes. Okay? So, I want to know the energy. Well, first let's get the power. The intensity is going to be 0.80 times the 1.4 kilowatts per meter squared. So 1.4 times 0.8, that's 1.12 kilowatts per meter squared. So if I take intensity times area, I'm going to get power. So I get 1.12 kilowatts per meter times 0.3 times 0.5, which is 0.15. So I get 0.168 kilowatts, which is, units of, here, hold on, erase for a second. So what I have here is 0.168 kilojoules per second. Now 60 minutes times 60, this is 3,600 seconds. So 0.168 kilojoules per second times 3600 seconds gives us 604.8 kilojoules of energy being absorbed. people talk about decibels. Okay? Decibels is a way to talk about the intensity of the sound relative to the minimum intensity for your ear to register sound. So decibels is 10 decibels times the log of intensity that you're hearing over I0. I0 is 1 times 10 to the minus 12 watts per meter squared. That's the minimum energy to get a signal to pass through your eardrum into your inner ear. Okay? And then that's just a really simple equation. Now guys, if you look at page 445 in your textbook, okay, it gives you a really nice table, okay, of intensities here for different things. So the threshold of hearing has a decibel reading of 0. But let's say a rock concert is 120 decibels. The threshold of pain is 130. So, you know, at a rock concert, you're pretty close to the threshold of pain. The loudest football stadium comes in at 140. So you're over the threshold of pain. Okay? So, lots of intensity on your eardrums for long periods of time actually mess with your hearing, and you lose hearing with time because of incredibly loud sounds. Okay, let me get things, make sure things are lined back up. Okay. All right, now, let's talk about the Doppler effect. The Doppler effect is a change in frequency received by a detector compared to the frequency of the wave emitted by the source, due to motion of the source and or the detector. Okay? The shift in frequency whenever one or both of the things are moving, the detector or the source, and or the source. So let's say that I have two people here, Nancy and Pablo. Okay? And they're looking at a source, they're listening to a sound, let's say, that's coming from a moving source. Okay? Now, the source is moving toward Nancy. So from her point of view, the wavelength is fairly short. But because it's moving away from Pablo, from his point of view, the wavelength is very long. Because before it makes the next disturbance, it's moved out. Okay? Before it's make the next disturbance, it's moved toward. So the crest emitted at time 0, time 1, time 2, from Pablo's point of view, are much further apart than they are from Nancy's point of view. Okay? Now, let's look at figure 20.26 on page 623 in your, wait a minute, old book number. Let's see, let me look at figure 16. Let's see, figure 26. No, we're fine. I already showed you that one. Although now it's in color. Let me show it, just give this to you again. Okay? You can see wave 1, wave 2, wave 3, they're in color. Okay? Longer here, shorter here. Okay, now let's look at equations. If the detector is still and the source is approaching, the new frequency is the frequency if the source was sitting still divided by 1 minus the velocity of source divided by the velocity of the wave. Okay? So S is a frequency emitted by the source, Vs is the speed of the source and v is the speed of the wave. For a receding wave, plus for towards, minus for away, it's s divided by 1 plus s divided by v. Okay? For a stationary source and a moving observer, if the observer is approaching, f plus, so plus for approaching, is equal to 1 plus v0 over v times s. The O here means the velocity of the observer. This is the velocity of the wave. For an observer moving away, f plus, okay, 1 minus v0 over v times f0. Okay? For light, the redshift is due to a receding light source, like a wave, a star moving away from us. The blue shift occurs in light as we're looking as an astronomer, as the light source is moving toward us. So we're going to look at problem 41 at the end of the textbook. Okay? So 41 is a Doppler problem. Problem 41 says, okay, a friend of yours is loudly singing a single note with a frequency of 400 hertz. Okay? While racing towards you, the velocity of the source of 25.0 meters per second. On a day when the speed of sound is 340 meters per second. What is the frequency you hear? And what frequency does your friend hear if you start singing? Well, let's do this point first. So in this case, we have a moving source. Now, because we have a moving source, I know which equation I have to use. So, if I have a moving source, and the source is approaching me, I'm going to use F plus is equal to F0 over 1 minus V source divided by V. So let's plug in here. Okay? So F plus is going to equal the 400 hertz divided by 1 minus 25.0 over 340. Now the units there are going to divide out, so I'm not going to worry about writing them in. So 25 divided by 340, negative plus 1. 1 over that times 400. So 432 hertz. That's the sound frequency that you would hear. Okay? Now, if we look at part 2 of the problem, now you're the source and your frequency is 400 hertz. And now, okay, the observer, the velocity of the observer is 25 meters per second. Okay? Because now we have a moving observer, Yeah, moving observer, and the moving observer is approaching. F plus is equal to 1 plus velocity of the observer over the velocity of the speed of sound times the frequency of the observer. No. Oh, frequency of the source. I don't know why they use O there. It should be, oh, the frequency of the source. So, F plus here is going to be 1 plus the velocity of the observer, 25 meters per second, over 340 meters per second, times the 400 hertz. So 25 divided by 340 times 1 plus 1 times 400. F plus here would be 429 hertz. So your friend is singing at 400 hertz, you're singing a note at 400 hertz. You hear what your friend's doing is 432 hertz. Your friend hears what you're doing at 429 hertz. We're pretty close. Okay, it's probably a round off error. So you can see moving toward moving away. And this, guys, ends chapter 16.